Have you ever asked yourself how you learned the workflow of a process yourself without any introduction? Have you ever played a video game without a demo level and you were still able to finish it? Have you ever been thrown into a situation without any background information and had to learn everything yourself without any guidance? Then you know that this is a complex task for your brain. And now imagine to mirror that behavior to your own servers and computers. Sounds futuristic and far, or does it? Welcome to my webcast, Reinforcement Learning 101. Today I'm your host, John Hassan Güntensberger, but you can call me John. I'm a data scientist and cloud engineer for AWS at Amanox Solutions and a machine learning enthusiast. Let's start our webcast by introducing you to our agenda today. We're going to start by taking a quick look into the general topic of artificial intelligence. In order to understand what reinforcement learning is, you need to know what AI is and where exactly reinforcement learning takes place in this huge topic of AI. Next, we're tackling the fundamentals of reinforcement learning on the example of the modern classic Pac-Man. And don't worry if you're not technical experienced developer, today you'll experience no code look-intos and no complicated mathematical formulas. Since reinforcement learning is so new and abstract, you might ask yourself, where can I use it outside of classroom use cases with video games? And yeah, good question. For that reason, we will dive into some use case, presenting you just multiple ideas on how to use it in your company. And as the last point of our agenda, I want to make a link to AWS, since I'm an AWS cloud engineer. Therefore, even you can start instructing your developers today on how to start your reinforcement learning experience in the cloud. Socrates once said, "I cannot teach anybody anything. I can only make them think." And I want to take a moment and let us set that statement inside our mind. As far-fetched as it may seem to make a link between artificial intelligence and this quote, you will realize in the next few minutes that it summarizes the behavior of AI well. AI, as it is today, has multiple definitions. Everybody, and in the same moment, nobody really knows what is really defined as. One of the key scientists in neural networks, François Chollet, calls AI a try to solve automized intellectual tasks that are normally done by humans. To simplify it a little bit more for you, we define AI today as the following. We talk about AI when dynamic decisions are made according to inputted, ever-changing and continuous new data based on experience of old data. This can be done in multiple ways, like a huge rule-based system or mathematical formulas. The modern AI that everybody is talking about covers those mathematical formulas that calculate an approximation for your data based on some complex calculations. So we are not talking about those huge rule-based systems I mentioned before. Those algorithms consist of three key components. Mainly A, the input that requests an intermediate action like a classification or an estimation. B, a freely changing part that tailors itself based on training data. This freely changing part can be a changing number in a calculation or a process order of action. And C, an output based on the calculation that answers the request asked by the input data. This could look a little bit like this picture I'm showing here. For this kind of mathematical AI, we differentiate into three types. Firstly, we have supervised learning. Those are algorithms that have labeled input data, which means that the targeted output is already defined. Here, the freely changing parts are so-called weights that are just dynamic numbers. Those numbers change based on the labels set for the data. Once the model is trained, it only receives new data without label, but knows at that point the pattern on how to output for those requests. Next up is the second one, unsupervised learning. In comparison to supervised learning, we don't have any labeled data. Instead, we make clusters, or in easy words, groups of data that match, at that point, unknown patterns. The freely changing part are those groups that vary based on your inputted data. The output then is either the group classification, or otherwise outliers don't match any group. In comparison to supervised learning, you often need somebody, a so-called domain expert or data expert, to interpret those data groups and assume on what new information was found. The last category is reinforcement learning, the third one. It is somehow in between of unsupervised learning and supervised learning. And this sounds confusing, but let me explain a little bit. We don't have labeled data to begin with. Often we don't even have a collection of data. Instead, the data is produced while the algorithm is running and learning. If we put that in a reachable example, just imagine we have a reinforcement learning agent that acts as a player, like a human. This player is playing Pac-Man right now. What we have then is an agent with a policy, and this policy is the equivalent to a strategy a human would have. That tells him how to play. An agent has the option to push any arrow key or the A and B button, like on a controller, as an action. We then have the Pac-Man game itself. This is called the environment. The actions from the agent influence the environment, and it changes the state of the game with each action made. The game then outputs after each action this new state, like Pac-Man and ghost positions on the game grid of the agent. Then we have the part that is somehow making the reinforcement learning a little bit supervised, namely the reward function. This is a function that outputs a number based on the action and the observations that were sent forward and backwards in that whole process. This number evaluates how good the action of the agent was, based on the outcome it provoked. It's somehow a feedback or a criticism. You can call it both. If we talk about Pac-Man, the reward could be really high if the agent wins the level, or real low if a ghost touches the Pac-Man and he dies. The feedback, or in other words, how well the agent played Pac-Man, is calculated from the action made by the agent himself and the history of observations returned by the environment, and next is consulted by the agent. Therefore, he adjusts his strategy until he plays it in the best way possible. After this explanation, reinforcement learning might sound a little bit like a classroom project. Something to play with, but no benefit for your business use case. At least that was what I thought when I touched this topic for the first time in my life. But I was so wrong. Right now, reinforcement learning is just the beginning, and it needs some time to settle down in multiple business use cases. For that reason, it's also hard to present a parade use case, because there is no parade use case. But I saw multiple occasions for the use case of reinforcement learning during my years as an engineer. So as a first use case, I want to present the classical one in the game industry, the personalized enemy. At least I call it that way. In classical game development, you have a fixed algorithm for a computer behavior that plays against you. It might not seem always that way, because the algorithm behind it is sophisticated, has some randomness behind it, and is really complex. But believe me, normally there is transparent, non-changing algorithm behind it. The personalized enemy I mentioned would be a new way to tackle computer behavior. If you start with a given classical algorithm, you already have a strategy in some way, or in the other words of reinforcement learning, what we learned is a policy. Given the basic build, the agent can now start adapting this strategy or this policy by reacting to your personal playing behavior. You can then design cool rewarding systems, like if the player has high health, then reward low. If the player has low health and dies like every third time, then reward high. The personalized enemy then learns during the game how to play against you, that you always feel challenged, but keeping the game experience still rewarding. But now I want to get away from those video game use cases, because most of you viewers are most likely not from that industry. An interesting use case, especially for the scientists and data scientists among you, are simulations. Simulations are useful for different purposes and can be of all forms, like economics development to find out the best strategy to influence the market, like physical simulations to master, for example, a perfect balancing of some peas on a spoon while the spoon is permanently moving, and then you mirror that on a robot. You see that exact use case in the GIF image here. Or like simulating traffic situation and driving behavior on streets, for which the learned is given to a car so that the car can drive autonomously. This sounds a little bit like that, what Elon Musk is doing with his Tesla cars and other car companies. So yeah. Even though I could go forever with my use cases and fantasize about it, I want to top it with the last presented scenario of automatic process optimization. And this is something that most probably many other companies could use too. In that use case, we think of the process workflow that you have, or the process itself, as the environment, where multiple variables change and one process step has influence on the whole process itself. And based on our understanding, if one input, here the process step itself, is influencing the whole environment, you can replace a rule-based process step directly with a reinforcement learning agent. If you think of a smart factory, for example, you could then build up a reward function based on multiple metrics like count of production damage, or waiting time between the steps, or even the produced cost by your process. It could be that the reinforcement learning agent learns that processing a product through the process step order A, B, C is slower or even more expensive than the process step order A, C, B. Oof, there was now a lot of theoretical knowledge presented to you. And at least I feel a little bit lightheaded now. Lightheaded like being in the cloud in my head, which reminds me that we have still our last topic open, reinforcement learning in the cloud. And man, I'm looking forward to present that to you. Since reinforcement learning is still young, there are no specific services tackling this topic except one, namely AWS Deep Racer. This service is an environment to start learning reinforcement learning by training an agent to drive a racing car automatically. This whole service is part of a racing league and more something to play with than something you really could use in your supply chain. So if you have some developers that want to get their hands dirty but not on something productively, this could be something for you. Otherwise, yeah. But at least I want to go a little bit into the internals before we settle to another service. And this service is built on 4 other AWS services, namely AWS Sagemaker to provide the racing simulation itself, AWS Kinesis to stream the video footage of the 3D racing simulation, AWS S3 to store the AI's metadata, and AWS Sagemaker, which we'll take a deeper look right now. If you want to engineer reinforcement learning system yourself that is business relevant, you want to get your hands on that service, believe me. Sagemaker looks on the service like your regular Jupyter notebook tool hosted by your preferred supplier, in that case AWS, but it's actually so much more. For all of you that never heard of Jupyter Notebooks, Jupyter Notebook is an open source web application that allows you to create and share documents that contain live code, equations, visualizations, and narrative text. It is actually an enduring runtime that can be multiple times invoked with newly live written code, and on top of it, you have a documentation functionality. That said, Sagemaker gives you those functions too, but there is so much more to discover. First of all, we are in the cloud, and therefore we can collaborate together inside the same notebook with multiple developers and scientists. This is amazing. Sagemaker itself provides multiple from AWS invented and Sagemaker native machine learning models and libraries that you can use to build your own AI. Additionally, you have new functionalities built inside the basic Jupyter notebooks, from which I can recommend 2 especially. One of those is the debugger for machine learning. This tool allows you to get insights into your AI and tracks down unwanted training issues. It might not be directly applicable to your reinforcement learning algorithm, but often those systems are combined or working with multiple AIs, where some are supervised or unsupervised learnings. And for those supervised and unsupervised learnings, the debugger matches perfectly the bill. The second one is the data wrangler. This one is especially useful if your environment loads data, ideally constantly, into the training. Data wrangler is a tool that aggregates and prepares data while loading it into your training environment. This is especially useful when multiple engineers work on the same environment and you want to provide the same data aggregation and preparation to all of your coworkers. Believe me, it will save hours of data wrangling via script. At least it did for me. So, there you have it. I hope you learned something new today. This was my course, Reinforcement Learning 101. If you have any further questions, don't hesitate to write an email to this mail address. It would be great if you give us a thumbs up and subscribe to our channel. My name is John Hassan Güntensberger, and I thank you for your attention. Have a nice day. Goodbye.